Chapter 2 Argand Diagrams Part 1. Argand diagrams. An Argand diagram is a graph used to represent complex numbers visually. A complex number has the form z is equal to x plus I multiplied by y, where x is the real part and y is the imaginary part. On an Argand diagram, the horizontal axis is the real axis and the vertical axis is the imaginary axis. So the complex number z is equal to x plus iy is plotted as the point x, y. You can also think of it as a vector drawn from the origin to that point. How to plot a complex number. So first of all, what we need to do is take the real part for the horizontal movement and the imaginary part for the vertical movement. The first example that we have is 5 plus 4i. This is plotted at 5 and 4. The real part is 5 and the imaginary part is 4, and this is on the y-axis. Minus 2 plus 6i is therefore plotted at minus 2, which is the real part, and at 6 for the imaginary part on the y-axis. And then finally for minus 7 and minus 3i, this is plotted at minus 7, minus 3, the real part on the x-axis, and the imaginary part on the y-axis, which is minus 3. The important thing to remember is that the positive real part moves right, the negative real part moves left, the positive imaginary part moves up, and the negative imaginary part moves down. Using these, we can imagine 5 plus 4i. Here what we would do is 5 to the right and 4 upwards. With minus 2 plus 6i, we move 2 to the left and 6 up. And minus 7 minus 3i moves 7 left and 3 down. Now we have an Argand diagram with 3 complex numbers. So these are plotted on the Argand diagram. There are 3 complex numbers. The complex numbers that we have are 5 plus 4i, minus 2 plus 6i, and minus 7 minus 3i. So 5 plus 4i will be plotted on 5, 4. On 5 for the x-axis and 4 for the y-axis. Minus 2 plus 6i would be here in minus 2 and 6. And then minus 7 minus 3i would be plotted as minus 7 and minus 3 for the y-axis. The horizontal axis again is the real axis and the vertical axis is the imaginary axis. So here is an example where we use an addition. So we want to add z1 plus z2, where z1 is equal to 2 plus I and z2 is equal to minus 3 plus 3i. So z1 plus z2, when we add them together, we end up with 1 plus 4i. How do we represent that on an Argand diagram? So first of all, z1 is at 2, 1, and z2 is at minus 1 for the x-axis and 3 for the y-axis. What we need to do next is place z2, so this vector here, at the end of z1, which is this vector there. So at the end of z1, that would give us z1 plus z2. The resultant vector is 1 plus 4i. So the final point is 1, 4. For subtraction, we do something else. So if we have z3 minus z4, so z3 is 3 plus 2i, z4 is 1 plus 4i. In this case, instead of having z4, we have minus z4, so we end up having 3 plus 2i minus 1 plus 4i. So if we have minus 1 multiplied by 1 plus 4i, we end up with minus 1 and minus 4, and we plot that here. And we do the same thing after that. So then we place minus z4 at the end of z3, so the vector z3. So this will give us the resultant vector, which should be 2 minus 2i. So the final plot should be 2 minus 2. So the rule here to remember is that for addition, join vectors nose to tail. So if we have the nose of z1 connected to the tail of z2, and then with subtraction we just add the opposite vector. So in this case we would have had minus z4. Modulus and argument. For a complex number z equals x plus iy, you can plot it as a point x, y on an Argand diagram. 2 important things describe that point. The first one is called a modulus. The modulus of z, written modulus z, is the distance from the origin to the point. So the formula would be the modulus z is equal to square root x squared plus y squared. So it's just the length of the line from 0, 0 to x, y. Vertical bars are the symbols. In complex numbers, they're called modulus bars because modulus z means the distance from the origin. So modulus would be for one value, whereas with moduli, we're referring to more than one value. The argument of z, written argz, is the angle from the positive real axis to the line joining the origin to the point. So modulus tells you how far away the point is, so it gives you the distance. Argument tells you the direction of the point, so the angle, or which way it's orientated. So here's an example. Z is equal to 1 plus square root 3i. This means real part is equal to 1. Imaginary part is equal to square root 3. So the point is 1 square root 3. So step 1, find the modulus. So modulus Z is equal to square root 1 squared plus square root 3 squared. Or modulus Z is equal to square root 1 plus 3, which is equal to square root 4, which is equal to 2. So the modulus is equal to 2. Find the argument. So now we have to use tan theta because we have opposite and adjacent. Tan theta is equal to y over x. Here tan theta is equal to square root 3 divided by 1 is equal to square root 3. We then do theta is equal to tan to the power minus 1 square root 3, which would give us theta is equal to pi over 3, which is equal to 60 degrees. Since the point is in the first quadrant, the argument is simply argument z is equal to pi over 3. The final answer for this example for z is equal to 1 plus square root 3i, the modulus, which is the direction, has a length of 2, and the argument, which is the direction, has an angle, which is pi over 3. So we can represent this on the Argand diagram for z is equal to 1 plus square root 3i. So we don't know what square root 3i is. What we can do is obviously start by plotting 1. So we can start with a dotted line going up through 1, and then we do know that the angle is theta is equal to pi over 3. So starting from the real axis is pi over 3. So we can imagine that. And then the length of modulus z is equal to 2. So we can draw a vector across from the angle in that direction with a length of 2 until it hits that dotted line of 1. So we can actually draw another dotted line that goes back to the imaginary axis. That should give us the point that we are looking for. Now what we're going to do is look at one example in each quadrant and how the quadrant changes the final argument. So for quadrant 1 we have z equals 2 plus 2i. So we start in the positive real axis and then the argument becomes 45 degrees when we meet with a vector. In quadrant 2 we have z is equal to minus 2 plus 2i. Again we start with the positive real axis and we meet with a vector and we get 135 degrees. With quadrant 3 we have z is equal to minus 2 minus 2i. Again we start with the positive real axis, we meet with a vector and then we get minus 135 degrees. And with quadrant 4 we have z is equal to 2 minus 2i, and when we start from the positive real axis and meet with a vector we get minus 45 degrees. And in each case all we're doing is changing the positive and negative of the x and y axis. So for z is equal to x plus iy, if x is more than 0 and y is more than 0, it ends up in quadrant 1. If x is less than 0 and y is more than 0, then we end up in quadrant 2. And then if x is less than 0, y is less than 0, we end up in quadrant 3. And finally, if x is more than 0 and y is less than 0, we end up in quadrant 4. So in each case, we always start from the positive real axis. And you can use this pattern here as well if that helps. But usually it's just that you start from the positive real axis and meet the vector, and then you take that angle. Now we're going to be looking at special cases where the actual vector lands on the axis, whether that's the real axis or the imaginary axis. If we have a vector landing on the positive real axis, for example z is equal to 3, the argument is always equal to 0. If we have a vector landing on the positive imaginary axis, for example z is equal to 3i, the argument is always going to be equal to 90 degrees, which is equal to pi over 2. This is because we start from the positive real axis, meet with a vector, and it makes a 90 degree. If we have a vector on the negative real axis, for example z is equal to minus 3, the argument is always equal to 180 degrees, which is equal to pi. So we start with the positive real axis, go around, and we meet the vector, and what we find is the argument is equal to 180 degrees. And finally, when we have the vector on the negative imaginary axis, for example z is equal to minus 3i, the argument is always equal to minus 90 degrees, which is equal to minus pi divided by 2. So again, we start with the positive real axis, we go around, meet with a vector, and we always have minus pi over 2 or minus 90 degrees for our argument z.